We've already learned that using time variation, that is the fluctuations of a time series over time, to infer general economic rules is very difficult and for many time series impossible. And that is because a time series is generated in a very different way from a cross-section that is collected by sampling randomly. In this video, we are going to discuss the conditions that a time series has to satisfy so that we can use it to gain economic insights. Let's think about the evolution of an economic time series. As an example, we're considering GDP growth in country C. GDP growth can be positive or negative, so let's put in the 0 line. Let's put ourselves in the shoes of green guy. Green guy is thinking about the time series before it starts. The time series will start here at t=1, and green guy is thinking about the time series before that. For green guy, the time series hasn't realized yet, so for green guy, the time series is a sequence of random variables y1, y2, and so on up till y_T. Now, as green travels forward through time, a universe will be drawn and the time series will be realized, and then green guy will slowly get to observe the whole time series. For example, the time series may realize like this. Let's call this universe omega naught. Or the time series may realize like this. Let's call this universe omega 1. Key is that we observe the time series in only one universe. So for example, if we are in universe omega 1, we will see negative growth in the beginning, followed by positive growth. Now, we will never be able to tell whether this kind of pattern was predictable from the very start in some sense, or whether this is driven by randomness. In the analysis of cross-sectional data, we also had randomness entering our regression equation through our error term. We took care of this randomness by repeated sampling. So essentially, we were able to look at this population from many different angles, or if you think about this population as the random experiment of drawing one random person, well, we observed the outcome of this experiment in many different universes. This is what allowed us to disentangle genuine economic effects from random variation when using cross-sectional data. If we want to do something similar for time series, then we have to find a way of accumulate information as we move through time. So we have to find a way to observe more than just one universe. Clearly, this is not possible for the whole time series, but maybe it is possible for small segments of the time series. For example, let's consider a segment of 3 consecutive time periods. In our time series, we observe many such segments. For example, the first 3 periods are these 3 periods. Traveling through time, we see more and more of such segments of 3 consecutive time periods. Under what assumptions do we accumulate information about typical behavior within these segments? Let's start by looking at these segments. Let's call them segment A and segment B. We now want to find conditions such that these two segments behave kind of like a cross-sectional sample of size 2, even though they are cut out from the same time series. To understand the first condition that we need, remember that we want to use these two segments to learn about the typical behavior of a segment of 3 consecutive time periods. So just to be able to talk about typical behavior, we kind of have to assume that this behavior doesn't change over time, so that the same economic rules apply here in the beginning of the time series as they do at the end of the time series. So in some way, the two segments have to be interchangeable. The way we formalize that is that we say, for someone who is thinking about the time series before it has started, these two segments have the same distribution. So the joint distribution of random variables y1, y2, y3 is identical to the joint distribution of random variables yt minus 2, yt minus 1, and yt. This means that ex ante, or before the time series has started, there is no difference between those two segments. They are ex ante identical. And this will be our first condition. And this assumption is called stationarity of the time series. The stationarity assumption restricts the behavior of the time series from an ex ante point of view. Our second condition will be about the dynamic behavior of the time series, so about information that becomes available as the time series is gradually revealed. Segment B happens after segment A has already happened. And since the past can influence the future, there's a possibility that what happened in A somehow influences what can happen in B. Our second condition restricts how connected segments A and B, or how dependent they are allowed to be. Specifically, we assume that A and B are almost independent if they are far apart, that is, if the distance between them is large enough. This ensures that what happens in B is not determined by the past, not determined what happened here at A. And this ensures that B reveals new information. So this way, observing both A and B accumulates information and behaves more like a cross-sectional sample of size 2 than a cross-sectional sample of just size 1. Condition 2 is called weak time dependence. Let's compare sampling in a cross-section and a time series. And here we assume that our time series is well behaved, so it is stationary and weakly time dependent. In a cross-section, we use random sampling. And instead of saying that we sample randomly, a lot of people say that we sample identically and independently. So a random sample is identical and independent. I will now demonstrate that the stationarity property corresponds to identical sampling and the property of weak time dependence corresponds to independent sampling. Identical sampling means that every cross-sectional observation yi draws from the same population y. So what is important here is that y does not depend on I. For a stationary time series, we can take any segment of consecutive time periods. So let's take a segment of 3 consecutive time periods. We could also be taking just 1, 2, 3, 4 time periods, whatever number, but we continue looking at 3 as we did before. So let's take yt plus 1, yt plus 2, so now we have 3. And under stationarity, this draws from a population that does not depend on t. Let's just say this population is y1, y2, y3. Or a different way of expressing the same idea is saying that any segment of 3 consecutive time periods draws from the same population as the first 3 time periods. Again, what is important here is that this here does not depend on t. Identical sampling for a cross-section or stationarity of a time series makes sure that we always learn about the same economic problem. So for a cross-section, the economic problem doesn't change as we move from one observation to the other. So the same economics apply to every observation. In a time series, the economic problem doesn't change as we move from one segment of 3 time periods to the next segment of 3 time periods. The same economic rules persist. So both conditions ensure that we observe the same economic problem again and again. Independent sampling in a cross-section. This means if we take any 2 observations yi and yj that are distinct, so I unequal j, then these will be statistically independent. So this means that observing yi first has no impact on the draw for yj. So if yj arrives after y1, then yj will bring entirely new information and will not repeat any of the information that is already contained in yi. Or in other words, yj will show us a completely different part of the population than yi. For a time series that is weakly time dependent, we can take our segment of 3 consecutive time periods and then we shift this segment by, let's say, s periods, forward or backward. So we'll have another segment of 3 time periods, yt plus s, and then the 2 consecutive periods after that. Under weak time dependence, these 2 will be almost independent, provided that the distance between them, so s here, is large enough. And here I'm intentionally being a little vague about what it means for the segments to be almost independent, or what s large means, so how large. So to get into the details, we would have to deal with a lot of mathematics that I don't want you to deal with. So we just focus on intuition. Weak time dependence means that we can observe this segment, and then if enough time passes, we can observe another segment, and what we will observe for this segment will not be pinned down by our observation of the first segment. So that means if we wait long enough, then new information will arrive. So both of these assumptions make sure that more observations also provide us with more information. So remember when I told you that in a cross-section, moving from one observation to the next is like randomly jumping from one element of the population to another element of the population. And these random jumps allow us to learn about all of the population. Now, in a time series that is stationary and weakly time dependent, moving from a segment A to a segment B that is sufficiently far away is like moving from one observation to the next in a cross-section. So that allows us to learn about the population in a way that is very similar to how we learn about the population in a cross-section. Now, I've spent a lot of time explaining why cross-section and these kind of time series are very similar. Let me now talk about how they are very different. So first off, when you have a cross-section and you collect the data yourself, then you can implement random sampling, and then you know that the data is identically and independently sampled. So random sampling is something that you can impose by design. On the other hand, for time series to be stationary and weakly dependent is a property of the economic environment. This is not something that you can impose by how you collect the data. Moreover, if you observe a realized time series, so you observe a curve like this one, it is not easy to verify whether it was generated by a time series process that was stationary and weakly dependent. There do exist some statistical tests that will allow you to test for particular kinds of non-stationarity, but there is no procedure that you can use to make sure that the data you have was generated from a stationary and weakly time dependent time series. So you should treat this similarly to an exogeneity assumption in causal inference, for example, where you have to argue economically that the assumption is satisfied and where you cannot use data to show that the assumption is satisfied. For time series, that is very important to think about whether a time series is stationary and weakly time dependent, because many time series that we encounter in economics are actually not. So these assumptions will fail very often in empirical practice. So what I haven't done so far is explained why these kind of segments are interesting. Let's compare this to the cross-sectional setting. So if I had a cross-section of countries for which I observe GDP growth, then I could use this cross-section to figure out, for example, the variance of GDP growth, right? To replicate this in a time series context, I would need only segments of length 1. And if the time series is stationary and weakly time dependent, I could use then the time series to figure out the variance of GDP growth. Looking at segments that are longer than length 1, so for example segments of 2 consecutive time periods, is interesting because it allows me to capture the dynamics of the time series that is something that doesn't really have any meaning in the cross-sectional case. To give an example of such dynamics, let's talk about autocorrelation. let's consider GDP growth today and GDP growth tomorrow. These are represented by our random variables yt and yt plus 1. So I may wonder, how are these related? How do these correlate? So if GDP growth is positive today, do I expect GDP growth tomorrow also to be positive, or do I expect it to be negative? So we have yt and yt plus 1, that's a segment of size 2. And wondering about the sign of the correlation is wondering about the behavior of such a segment of size 2. In particular, we are wondering about the covariance between those two. Without stationarity, this covariance could potentially depend on t. So to specify the question whether GDP growth today and GDP growth tomorrow are related, I would first have to specify in what time period. But under stationarity, this covariance is independent of t. In our realized time series, we observe many segments of size 2, this one, lots of segments of size 2. And for each segment of size 2, we observe GDP growth today and GDP growth tomorrow. And here's another one. So here we observed today positive GDP growth and also tomorrow positive GDP growth. And here it's sort of the same relationship. Now if the time series is also weakly dependent, then observing the same relationship here as here is actually new information, so that we can be kind of sure that this is a general pattern rather than just a pattern that we saw once randomly. So this is how stationarity and weak time dependence let us define the concept of an autocorrelation and let us figure out the sign of the autocorrelation from a observed time series.